So now I can start recording. Now the videos I'm going to upload, I'm going to have a better quality, but you are not going to be able to see me. You're just going to hear my voice and see the screen. Okay? Let's minimize this. And we were about to talk about. This is homework number 2. This is problem 1. It's a problem of bulk mass density, which in general is going to be the density of the mineral part times 1 minus porosity plus the density of the fluid times porosity. The density of the mineral, remember, is going to depend on the volumetric fraction of, say, quartz, calcite, clay, anything. And the density of the fluid is going to depend on, for example, saturation of water, saturation of oil, saturation of gas. What you should remember from here is that always this density is going to be more or less 2, maybe a little bit less than 2, but never bigger than 3 point something in terms of specific gravity. So if you get something which is way outside the range from 2 to 3, there is something wrong. Okay? Okay. Then no question about this one? Let's go to the next one. In this particular problem now, what you have to do is you have to calculate total vertical stress, but with a profile of density which is not constant. Okay? So let me just copy some numbers over here, and then I'm going to switch to the dog camera. But the problem basically consists on going to 1,000 meters. Be careful here about the units, because I'm mixing the units, and I'm doing that on purpose so you become familiar with both metric units and field units. Alright, so I'm almost there. Okay, so this is what the problem says.
I have a question.
Yeah.
For this one, it doesn't say what units to put your answer in.
Anything you want.
Oh.
Okay, anything you want. So either the SI or the field units, those are fine. Okay, so in this particular problem, we have a profile of density which is not constant, and you have to use the integral equation in order to get the right value of vertical stress at this point. But the main idea of this plot is that you know that the vertical stress is going to be all the area underneath this times G, right? There is something that I didn't specify in the problem, and I'm telling you right now, if you did it, if you use some other number, that's still okay, don't worry, okay? But if you haven't solved it yet, I'm telling you that when you get to the seafloor at 1,000 meters, this value is 1800. When you get after 500 meters below the seafloor, this value goes to how much it was? 2,000? to 350, increasing linearly. And when I didn't tell you here is that this one was 1000. So you can assume here 1000. That's fine. Yes. That's fine. That's fine. Yes, that's fine. All right. So since the integral is going to be the area of all these density plot, then what you have to do is SV is going to be equal to 1000 kilograms per meter cube times density times, in this case, it's going to be 1000 meters. Let me kill the focus. Okay, let's move this thing over there. Plus, so this one is the first square. The area of this part is going to be the average between that point and that point. I'm not going to write everything because you're supposed to do that. Okay, but I'm telling you now, what is that going to be? That number plus the other number there divided by 2 times, that's a very weird G. I don't know why I did that. I'm writing a rho. This should be a G. Times 500 meters plus, now that we get again to the constant part, just 2, 350, and so on. Okay, I'm not going to write everything, but now it should be just the distance from here to there. I heard a lot of discussion about G. Do I include G? I don't include G. How do I do this? If you're going to use metric units, and in the metric system, International Metric System is called also the MKS system. And why? Because it uses meter, kilogram, and second. As long as you use always these same units, your result, in this case for stress, is going to be in pascals, which is equal to the Newton divided a meter square. So try doing this. Use kilogram meter square, use meter. For acceleration of gravity, you're going to have to use 9.8 meter per second square. And if you multiply all of that, your result should be in pascals. Okay? Probably you already have the solution for this, or you could do it right now. But let me give you a few other hints to know if your result is okay or not. Here we're getting to 10,000 feet of depth, right? If this were to be onshore, what would be the total vertical stress? More or less. If it were to be onshore, it's not, okay? But I'm just telling you now. 10,000 psi, and since it is onshore, it's going to be less than that. So, I don't know, let's say 8,000, something like that, okay? Always your values of vertical stress in your problems are going to be in the order of 1,000 psi, from 1,000 psi to a few tenths of 1,000 psi, but not a lot more than that, not more than 20,000 psi. If you get 100,000 psi, that's a lot. There's something wrong. Okay? So, values of SV in general, and let's be a little bit more generous, are going to be less than 20,000, 25,000 psi. Sometimes maybe a little bit more. but not a lot more than that. And in the same sense, your values of SV are going to be generally lower than 150 MPa. So if you get something like 1000 MPa, that's wrong. Always these values are going to be in the order of a few tenths of MPa. And for this particular case, we have about 3 kilometers. 3 kilometers, if you were to be onshore, will be about 70 MPa. But this is not onshore, it's offshore. So the answer should be around 60 MPa. So try to do all these numbers in your head, just to get an idea about what you should get. And after you do all your computations, that number should be around those numbers that you do with the gradients that we learned, 1 psi per foot and 23 MPa per kilometer. So the answer here is going to be about 60 MPa. Alright? Any question about this problem? Should we go to the next? Okay. So the next problem, it's a little more difficult. And here, now you're going to need the help of Excel. And with Excel, what we have to do is go bed by bed and use the density in order to calculate vertical stress. Let's see if I can do this quickly. I'm going to copy all of this. Let's see, Excel allows me to paste that right there. Okay, let's see. Okay, this is fine. Alright, so what do we do now? We have density, we have depth. The first thing that we can do is calculate and this is the workload, remember. Always calculate first the vertical stress. And in this case, the vertical stress, first we're going to use the metric units, since we already have metric units here. In the next problem, we're going to use field units. And this is going to be simple. The first one is going to be 0. And let me show you a little more so you can see better. The second one is going to be the weight of the layer on top of what I'm looking at. And that's going to be the average between these two plus 9.8 times the thickness of the layer that I have right on top. And that's going to be this number, that number, okay, and that's going to be that in pascals, okay? I don't like looking at pascals, so let's convert it right away to MPa to see if I have something that makes sense. I don't like when it makes these corrections. Alright, so 1 megapascal is going to be a pascal divided by 1 million, right? So I'm going to multiply this to 1 to the minus 6, and here I should get 1 MPa. And that makes sense. 100 meters, that's going to be 1 MPa, because in 1 kilometer I have 10 MPa. So in 100 meters I should have a 1 MPa. Just to verify that everything is okay here, let's also try this on feet, just to compare. something completely very crazy. Divide is 0.3480, and if I continue this, okay, so 100 meters, 330 feet, and if I have 330 feet, let's also put this in terms of PSI. 1 MPa is going to be in PSI, I have to multiply it times 145, and that's going to be the number in PSI. So look at these two numbers now, this one and that one. You remember the ingredient of pore pressure was 0.44, so 0.44 is about half. Half of this is 150 or so, and here we have 135. It makes sense too. Alright, so now that we know this is good, we're just going to copy it to the entire there, and I'm going to copy this too, and there is a problem here. I forgot something. Anyone can tell me what I forgot? Add the previous set, right? So I forgot, since this is an integral, remember the integral is going to be the entire element. But I need to add the previous set. So the first number was good, but the others were not. Now it's an integral. Before it was just the area of each specific layer, or the grade of each specific layer. And now I have here at this depth 37 MPa, and that kind of makes sense because let's do it in PSI too, so we verify the two of them. At 6,000 feet of depth, I would expect at most a value around 6,000, but since this is offshore, it is lower than that. And if I were to work in metric units, at 2 kilometers, I would expect a maximum of 46, but this is less than that because it is offshore. So the SV, I'm pretty confident that in this case it is good. And the next step will be to plot that. And what I want you to do is to plot, figure out what's going on with this keyword. Okay, I think I figured it out. That's not doing that I want. No. So you grab your delta and do the scatter plot, and this is the profile of density, okay, but that's not what I want. You can do that also at profile of density, but here I want to plot SV in the y-axis and depth in the x-axis. So I have depth, no, that's not it. Okay. Okay, now I have, and what I'm going to ask you to, because this is the way this is usually done, is to plot depth in the y-axis in reverse order, meaning that depth is going down, and whatever you're plotting on the x-axis, which in this case, this one is SV. In nameplate. And I'm asking you also to do the same thing in field units in PSI. Alright, so we've got the value of SV. Any question about that? No? That's the easy part. Now what you have to do is to use this value of porosity to compute a pore pressure. And let's call this one the real pore pressure. And let's call this one the hydrostatic, which it might not be true, but anyway, just to have a reference, we'll plot it. Okay. So this is pore pressure. If it is hydrostatic, then simply what we're going to do is we're going to use the same equation that we had before. I'm going to simplify one step here, which is I'm not going to put in MPa, I'm going to plug it directly in megapascals. And I'm going to use, so it should be density. Remember, this is water, right? Divided by 2 times 9.8 times difference in depth times 1 to the minus 6. Alright, I get 1 MPa. I go to 500 meters and I get I forgot again to add the previous value. I should get to 5 MPa around here, and this is water, right? And what I'm going to assume is that after this point, I don't have water anymore, but I'm going to assume that the density is just the last value of water density. Okay? So you see what I'm doing here? I'm just, instead of using the bulk density of the rod, because that's the data that I have, I'm going to use the data of the density of the water, which in this case the last value was 1031. And if I do that, this should increase to more or less 20 MPa at 2 kilometers. And if I add that plot over here, the hydrostatic pore pressure now is going to be that. So now I have pore pressure and I have vertical stress. But this is not a real pore pressure, okay? This is just hydrostatic pore pressure. I'm assuming that that's a value that I have, and in order to make sure that you don't think this is real, let me change what we see over here. I'm going to put this as a dashed line, let's do a dotted line. I'm going to put no marker. Okay, so why didn't change? Oh, just selected that part. Alright guys, do you have any questions?
I have a question.
Yeah, go ahead.
Can you show the equation for the
What, just one sec. Okay, that's what I wanted to do. Here? So, here, what I did was, let me zoom in first. What I did was, instead of using the density here, because I'm starting to get into the rock density of the rock, I just continue using the density of the water. And I'm going to assume that the density of the water inside the rock is equal to the density of the water in the part where it's no rock, and in which I knew the density because I had that data. So this is a little bit more sophisticated than just assuming, let's say, 10 MPa per kilometer, but the values are almost the same. So if you see over here, for example, 13 hundredths of depth meters of depth, I have 13.1 MPa. It's very similar. All right. So now where it gets a little bit more complicated, it's over here, because now in this region in which you have a shale, now you have to compute the real pore pressure, and that's going to come in here in this other column, okay? And before you do that, you need to compute what is the effective vertical stress, and that one you have to compute it using this equation over here. Let me find it. Okay, it's basically this equation, but you solve for sigma v. We saw that in the notes how you do that. And once you get sigma v, you're going to be able to calculate pore pressure by subtracting, you know SV, you know sigma v, pore pressure is going to be SV minus sigma v. And what you're going to get is something very similar to this plot, in which you have the total vertical stress, also called lithostatic stress. There is an assumption of hydrostatic pore pressure, and at some depth, that the real pore pressure is this line over here, and that tells you the actual pore pressure. You can also plot porosity, and it's going to look very similar to this plot as well, in which porosity may be going down, but then starts to increase, or it may stay more or less the same. And in your assignment, in your problem, that's going to start more or less at 1200 meters. So in this particular plot, around somewhere over here, you should see that your pore pressure at this point is going to be more or less hydrostatic, but as you go deeper, it's going to deviate from that. And that's going to be the actual pore pressure. And are going to be the values that you're going to compute and you're going to plot with this column. Okay? Any question about this? I'm gonna finish here. If you don't have any question, I'll go to the next one. Okay? Because the next one, we have 20 minutes left, and it's the most difficult one. But let me tell you that the next problem is exactly the same as this one, but just with a lot of data. That's it. Okay? All right. So let's go to the last one. For the last one, we need to download some data. I need to go here later on. I'm going to go the easy way here, and I'll go to undergraduate homework number 2, and I'm going to download this file. I forgot how to download these files, but I'm just going to do this one. Let me see if I can work it with Shift.
If you want to download it,
yeah.
Go up, go all the way up.
There's usually a download link, but when the file is not,
you can just right click. Go to raw. Yeah. Right click.
But there is no raw. Oh, okay,
Yeah,
here.
Yeah. Oh, sorry.
Oh,
Right click the raw.
oh no, this is good. This is good because now you go raw, and then you go here into save as. Where's the save as?
Yeah. So. So. Yeah.
Oh, here, save as. So, and then that's a DAT file, okay? So, okay, let's save that, and okay, done. But I'm gonna just do this. It's gonna be even easier. Control A, Control C. I'm going to open here a new one. And I'm just going to paste it, and that should be it. Okay, guys, do you know this trick? Sometimes, you can paste something, and it doesn't look like in columns. This is something I learned very recently. You go from text to columns. And here is like importing a file, and you put here delimited, and then in this case, this is separated by space, and that's it. All right. Yeah. What? Yes. Let's do it one more time. So you have your file that, in a simple column, you have all the data. So if you want to separate it, you go data. In data, you go into text to columns. And in text to columns, it depends on the file, right? Sometimes it may be fixed width, sometimes, and most time, it's going to be delimited. So you click delimited, and then in delimited, you choose what is the delimiting character. It might be space, it might be semicolon, it might be comma, it might be anything. And in this case, it is space. So, and then just click next, and finish. And well, it did just one column. So let's do it again. Okay. So let's try again. Oh, I didn't like that. I don't know why. Well, let me try selecting everything. All right. Okay, so we're there. All right, this is bulk density. And I have the file now. All right, so let's see. The first thing I'm going to do here is I'm going to get rid of all these odd values that actually mean no information, okay? So you go Control F. I'm going to do replace 99.25. And I'm going to replace with nothing. And replace all, okay? They disappear. So Control F and then replace, and then you look for what you don't want, and then on the okay, I can do that again. All right, so let's go again. Control F, okay? So you're on your computers, you do Control F, and this window is going to pop up, and instead of doing find, you click here and you go and replace. I don't know if in Mac might be a little bit different, but there should be something to find and replace. Let's see if we find it here. So data.
Just Control F.
Just Control F. Well, but you don't have a replace. You don't have a replace tab.
No, you do.
Okay. But I hear some people don't have that replace. Okay, well, you hit replace, and then where it says replace with, you put nothing, okay? You put nothing, and then you hit replace all, and all those disappear. And that's very good because now you know where your data is and where you actually have data. For example, I'm in this cell right now, and I'm going to press Control and move the arrow down, and it will go to the first point where I have data, which is in column row number 120, or the same one in which I have BP, or in the one I have VS. Well, in this case, density. All right, so you can play with Excel later on. Let's see how we calculate vertical stress here. And now I'm going to compute in PSI. All right. the first thing I'm going to do is I'm going to assume that, notice that this log file starts at 1864, okay? So I know this place is on shore. And since I don't have data at this depth, what I'm going to assume is that everything above the actual data, it has the same density. I did something similar before in the case of the water, right? In the lack of data, I'm just going to do this assumption. So I can start working from here. I could have started working from the other point, but let's just start from there. All right. So the first point of vertical stress is going to be equal to the stress gradient, which we know it's close to 1, right? Let me zoom in so you can see the equation a little bit better. We know it's 1, but we know it's 1 whenever the density of the rock is 2.3 grams per centimeter cube. So in this case, it is not 2.3, it's 1.8. So it's going to be a little bit lower. So simply what I'm going to do is I'm going to use this value divided 2.3, and now what I have just written should be something like 2.0, something like that, which is less than 2.3, that because the rock is less dense than that. And finally I multiply times depth, and this is my value of total vertical stress. Let me decrease the decimals, and it kind of makes sense, right? Because the rock is lighter, so it's not 1800s, it's 1500s. All right, so that's my first point. In our problem before, the first point was 0. In this problem, it's not 0. Okay, let's go with the second one. The second one, and now I'm not going to forget, is going to be the one immediately above plus, again, the gradient. And now I'm going to use the average of the density in the layer above divided 2.3, because 2.3 will be 1, times the difference in true vertical depth. Now I'm going to use just measure depth, okay? But I'll come back to this in a bit. But now, just as an example, let me finish this, and I'm going to use depth as that. So each layer in this case is 0.5 feet. So I'm adding each layer, which is 0.5 feet, and this is the result. And if I just copy that, if you guys don't know, you know this trick, you click in the corner there in that square, double click, and then copies everything down. All right, so let's just check that we have numbers that make sense. And also let me move the decimal. Something very important that I still see a lot in students that are graduating and are seniors is that still you don't understand very well, some of you, not all of you, the concept of significant digits. If I were to tell you that the vertical stress is 1477.423, that's totally meaningless, because we have a lot of uncertainty in this measurement, and probably is, I don't know, the plus minus 50 psi. So given this number, it doesn't make any sense. That's why I'm just going to provide this in psi. All right, so let's see. I'm going to go to the bottom of the data, and I see that at 7,500 feet, I have 6,800 psi, which kind of makes sense because it's lower than this number. The rock is lighter, so that makes sense that I think this number is okay. So I have vertical stress, but there is a little thing here that you need to do additionally. Okay. We said that measured depth is not true vertical depth. So I'm going to add a column here, which is going to be TVD sub C, and this is going to be in feet. And where I'm going to get this information from the deviation survey. All right, so let me get there. Deviation survey, and this is the data. I'm gonna go raw. Thank you for the trick. I didn't know that. Copy everything, and here I'm gonna put in this same tab rename deviation survey. Just copy the data. I'm gonna do the same thing as I did before. Text to columns, delimited. Next, finish, and now I have the API number of the well. This is this first number, unique wellbore identifier. I have the name of the lease, I believe, or let's see, let's go down. BLD, I'm not sure, but anyways, I have here measured depth. Oh no, I know what happened. There was an offset. So, okay, it's BLD number 10. That makes sense. But the third column is measured depth, which is 0, 100, and the fourth column is true vertical depth. So this is like this. You see that there is an offset there of 3 columns, so this should go here. Okay, and we don't need this, okay, so we're gonna get rid of it. This is what I want: measure depth and true vertical depth. Okay, we need that relationship. So what I'm going to do is I'm going to make it easy just for this example and create a correlation between those two, between MD and TVD sub C, and that's going to tell me what is the TVD as a function of measure depth. Okay. And with this equation now, let me add the axis just to clarify what I have here. Here I have MD in feet. Here I have TVDSS in feet. And what this equation is telling me, and it has a very good fit, which is not going to be always the case. This well is almost vertical. That's why it works, okay? But it's telling me that with this equation, I can calculate what is TVD as a function of MD. Notice that these are negative values, okay? So I'm going to have to add a negative in my equation. But I just copied that equation, and I'm going to put it here. And since that was a negative, the X now is MD, and that's my true vertical depth sub C. And it makes a lot of sense that that depth is less than the MD, right? Because the wellbore is going to deviate. Again, just copy everything, and now instead of using MD, I'm going to use the correct value, which is true vertical depth. And I need to correct that one, and I need to correct this one. And I need to correct the rest as well. And now that I have all of that, I can plot true vertical depth as a function of SV as a function of true vertical depth sub C.
Which ones did you grab?
Just one sec. I'm just selecting something. Just one sec, guys. I'm just selecting something, and this is the way I like to do these plots. Just select anything, but then once I have control over that, I have that. This is what I wanted to plot. So now we have here true vertical depth in the y-axis and SV in the x-axis. You will have to reverse that, and where is that? Reverse order. Okay, and that's the solution. Okay, so one more thing, guys. This well is quite vertical. Okay, in Canvas, I uploaded a fresh new file from the Permian Basin that includes a wellbore which is first vertical, and then it goes into a lateral direction, and you will see that what we just did is not going to apply, but if you check this file, it's the same as the other one, and you will see how at some point the lateral kicks off. Alright, I'm still trying to get the LSA file for this one, but I don't have it yet. Alright guys, have a great weekend. I'll see you on Monday. Please turn in your homework today. Yes.